The question should be gone. There we go. Yeah. Yeah, last year it was kind of strange that there were 3 civil engineering exams all in one day. So I offered to move mine, but it was the way it worked last year. Is I said we'll move it, but everybody has to agree, and that's why I did it that way. Okay, everybody. I hope everybody is prepared for the eclipse. I was saying this beforehand. Most of the convenience stores and gas stations around here are selling eclipse glasses in case you want to go check it out this afternoon. Okay, we are down to the wire, folks, because we have today's lecture, Wednesday's lecture, Friday's lecture of this week. Next week, we have lecture on Monday, a virtual lecture on Wednesday, an exam review on Friday. And then beyond the final, we are done. This is it. That is done for steel design. So we are down to the wire, folks. I wanted to mention a couple things. So first off, as I do every year, I posted a brief assignment on Blackboard for you to do the course evaluation. As I say every time, you all could say I'm the worst professor ever, and that's fine. I just want you to do it. And if you upload proof that you did it, I'll add 10 points to your overall homework average. So it sort of rounds out to an extra point in the class. But I wanted to give everybody an option for that. I am tinkering with the idea of, instead of teaching steel next spring, teaching timber. I haven't made up my mind yet, so I'm thinking about it. So I have a feeling that'll pop up in the evaluations, but I've been thinking about it. If you want to take timber design, just get used to a bunch of tables. Tables upon tables upon tables upon tables. Because you got to look up flat use factors and moisture factors and temperature correction factors, and yeah, it's a lot of factors and a lot of tables. But we might do that. Okay. I know we still got a little bit of homework to grade 6-1 through 6-4. I would ask you how the homework went this weekend, but you didn't have one. That was on purpose. Today what we're going to do is continue the analysis phase of lateral torsional buckling, and then we're going to introduce design. I'm going to go ahead and tell you today that today's class is going to feature some wild equations and some wild design aids, okay? So I really do think it is in your interest to get your calculator out today. We're going to do one calculation that is a bit, it's a bit long, and I kind of want you to get, that's a technical term by the way, and I want you to get comfortable with it because it is an equation that you might see again, and so I just want you to see how it works. Okay, so this is our AISC flowchart for LTB, and really all this is just the LTB curve written in a flowchart fashion. As I said last time, I really want you all to make your own formula sheets and write them your own way. That being said, I do kind of understand if this flowchart kind of just gets, placed on your formula sheet, because I really did a lot of work to sort of collect everything in one, hey, here it is, flowchart. So basically the idea is you take your unbraced length and compare it against the 2 anchor points LP and LR. And dependent upon what zone you're in, zone 1 is if it's less than LP, zone 2 is if you're between LP and LR, and zone 3 is if you're greater than LR, we can compute the capacity directly. And most of these terms are either going to come from table 3.2 or table 1.1. Table 3.2 is the ZX charts, and table 1.1 is just where all the properties are. I did want to mention a note on lateral torsional buckling analysis in general. So up until now, we've been doing what I would say are really simple problems, if that makes sense. Like we've had a simply supported beam with a uniformly distributed load, or maybe a better way of putting it is up until now we've been doing problems that can be categorized based on the structural analysis aids. Like table 323, we just find one of the cases and use those. Well, what if you have a problem that's like this? This is a really out there problem. We don't have an analysis aid for this. For this problem, we'd have to draw the shear diagram, draw the moment diagram, and sort of do it for real, okay? If we look at this problem, I have a beam that it's an overhanging beam with all sorts of different loads. If we look at this beam, there are 3 different segments, right? Each one of these segments has a unique unbraced length, a unique LD value. Each segment is going to have a unique CB term, okay? So if that's the case, each segment is going to have a unique FMN, and also each segment has a unique maximum moment from the moment diagram, okay? So the way that this would work is if you were analyzing this beam, what you would do is calculate a performance ratio, an MU over FMN, for all 3 segments, okay? So you have a performance ratio for this segment, performance ratio for this one, performance ratio for this one. And all that would be is just the MU is going to be the largest moment from the moment diagram from each of these segments, and FMN is just calculated FMN for each segments. That's how you would handle moment. For shears, what you would do is you just use the maximum shear overall. And I say this with the caveat that that's if shear is like what we've been doing so far. In other words, where shear just hasn't really been a problem. If shear becomes a problem, well then shear design becomes a unique animal in and of itself. But if shear values are relatively low, just use the maximum shear for a performance ratio. For deflections, just use the maximum deflection along the entire beam to check against a limit of L over 360 or what have you. Does that make sense? Are you good with that? Okay. All right, let's do another example. I'm going to give you a W14 by 61, and I want to compute the flexural capacity. Now, a couple things about this. Let me pull this up here. So, a couple things I'm telling you. The unbraced length for this is 30 feet. And I'm going to go ahead and give you the CB value. CB value is going to be 1.5. I want you to express your answer in foot kips. And I want to give you a note. Okay, so W14 by 61. So the first thing that we need to do is we need to figure out what zone we're in. Zone 1, Zone 2, or Zone 3. And in order to do that, we need LP and LR. Okay, so we want to look up LP and LR for a W14 by 61. But I'm going to go ahead and tell you the W14 by 61 is not one of the bold rows. Okay, it's not one of the bold ones. So it might take a little bit of time to find. And there's a reason we're not using one of the bold rows. And that'll make sense a little bit later. So what I want everybody to do is open up the ZX charts and let's see if we can find the W14 by 61. And for that W14 by 61, let's see if we can determine LP and LR. Has anybody found what page that's on, by the way?
325.
325. So, what is LP and LR, by the way?
8.65 and 27.5.
8.65 and 27.5 feet. Everybody else able to find that? Okay, so if that's the case, hold on. Let's try that. Okay, so LB, what is LB for this problem? That's my pen. Thin all of a sudden.
30 LB.
Say it again, 30? Oh, my pen decided to be difficult all of a sudden. I don't know why my pen's doing this. 30 feet. Okay, so if LB is 30 feet, what zone are we in? Zone 1, 2, or 3? 3, right? Because here's the thing, right? So here's our, chart, right? This is LP, this is LR, so this is zone 1, 2, and 3. And our LB is like right here, so we're in zone 3, okay? So what we're going to need to do is compute capacity according to the elastic solution, okay? And I'm just going to tell you this equation is a little messy. What's that?
Oh, never mind. We got it.
What I do?
No, it was nothing.
Oh, okay. If that pen was covering it, my apology. Okay. Why is my pen getting thin all of a sudden? I didn't do anything. I don't know why my pen's being strange this morning. Okay, so for our beam, okay, the first thing that we know is C sub B. Okay, C sub B is 1.50. That was given. Okay. The other thing that we know is LB is 30 feet. Okay. Now, I'm going to go ahead and tell you right now, go ahead and convert this to 360 inches. Okay. That's very important. Go ahead and convert. All right. Now, there's a couple of other parameters that we're going to need. I'm going to look into the crystal ball a little bit, but we're going to go to table 1.1 for the W14/61 to find these. So we got to go to the front part of the manual, okay? And for a W14/61, I need the following quantities. I need SX, I need H naught, and I'm going to explain what these are here in a bit. I need RTS, and I need J. And by the way, these all come from table 1-1. All right. So somebody help me out. What is the section modulus for a W14/61?
92.1.
92.1. And what are the units?
Inches cubed.
Inches cubed. Okay. H naught. What is H naught? It should be about 13 or 12 something.
13.3.
13.3. Just so everybody is aware, H naught is, so if here's your I shape. Here's your I shape. This dimension right here is D from the top up to the bottom, but from the center to the center, that's H naught. So H naught is from the center of the flange to the center of the flange. So it's a little bit less than 10. Okay, RTS is
32.8.
RTS? That's Z.
2.7.
2.78? Yeah. RTS is a radius of gyration for lateral torsional buckling. So what we're going to do is compute an L over R, and that's going to be the R. So that's one reason why we need this in inches and this in inches so that the units cancel. And finally, what's J?
2.19.
2.19, and it's inches to the fourth. Okay. If the moment of inertia is a flexural stiffness, then J is a torsional stiffness. And there's two torsional terms. There's J for pure torsion and CW for warping torsion. So there we go. Okay. So what am I doing here? I am ultimately going to compute the critical buckling stress, and I'm using this equation right here. Okay. So like I said, it's a little bit of a mess, and unfortunately, like with elastic buckling, there's no pretty design aid that can help us out with this. We just kind of need to muscle our way through it. So FCR is CB pi squared E over a slenderness squared. And then we've got a square root over here. I'm going to hold off to actually draw the square root sign. 0.078, we have a fraction. And then that's slenderness squared. That's the square root of all of that, okay? So like I said, this is just a really big equation. We just kind of need to muscle our way through it, okay? So I'm going to move this over a little bit because I want to make sure I got plenty of room here. We're going to talk about units here in a second and how it's really the units for E that define the units for the whole thing. And C is 1. Don't forget to square your slenderness values. Okay. So that is our expression here. Okay. Again, unfortunately, there's really no shortcut to it. We just kind of have to muscle our way through it. From a units perspective, here the units cancel, here the units cancel, and inside this bracket right here, we have inches to the fourth over inches to the fourth. So everything over here is unitless. The only thing that has any units when it's all said and done is the E value. So our answer is going to be something in KSI. So again, this is just kind of a mess. You just kind of have to muscle through it. We'll see if anybody has an answer for me on this one. Everybody have a number for me? Again, I just kind of think you need to do this once to make sure that you're comfortable with it.
126.4.
Say it again.
126.4.
That's not what I got.
46.77.
That sounds right. 46 point, is it like 779?
Yeah.
Yeah, I got 40, that's what I got. I got 46.779. What I would say is check and make sure that your groupings, that you got all your parentheses, check and make sure that everything is supposed to be within the square root as it's supposed to be, and make sure that these are squared. Is everybody else getting that 46.779? That's the answer, okay? Once you get that, the rest of it's pretty easy, okay, because the rest of it is just phi mn is phi times FCR times SX, but actually that's not correct because really what it is the minimum of that in MP. So actually, let's do this. Let's do it this way. Bless you. Let's do it this way. Let's first calculate FCR SX. Okay, phi FCR SX, which is 0.9 times 46.779 KSI times 92.1 inches to the third. Now, by the way, when we do this, what are the units going to be in? This is a moment, right? This is a moment, okay? KSI times inches to the third is going to be inch kips, right? So what I'm going to do is I'm going to say, okay, I want this in foot kips. So I'm going to divide by 12. So what is 0.9 times this times 92.1 divided by 12?
Um, 323.126.
Okay, so we'll call it 323.13. And this is in foot kips. All right, everybody with me on that? Now, what I want you to do is, for our beam, can you also tell me what phi MPX is? What is phi MPX?
383.
383. Why am I looking up 383? Like, why do I care about that value? Well, I care about that because phi MP is the absolute maximum flexural capacity that the beam can withstand. Because remember, this is the LTB curve, but really the LTB curve looks like this, right? And I'm trying to figure out, because I don't have a plot, I'm trying to figure out this is the actual capacity. Is this value less than MP or not? Okay? Because here's our flow chart, right? Our flow chart says that the nominal capacity is the minimum of that in MP, and that's what that cutoff is right there. So therefore, phi MN is the minimum of that and that. So our flexural capacity is what we just computed. That's our answer. And by the way, this is exactly what we did last time, right? For our last example, we said that phi MN was the minimum of a pile of junk or phi MP. And that's kind of what we're doing here. Phi MN is the minimum of this or phi MP, because I don't care what's going on. CB, so what's happening is here's our capacity, and CB is serving to increase our buckling stress, right? But you cannot increase it beyond MP, okay? So that's what's happening right here, okay? Does that make sense? Is everybody okay with that? I mean, again, like, here's our zone. So anytime you're in zone 2 or zone 3, the capacity is the minimum of something and MP. The minimum of something and MP. That was a lot of heavy math for 9:15, 9:20 a.m. So is everybody good with this? Yes.
For JC in the FCR calculation,
Yes.
C is 1.
C is 1, yes. C is 1, so I'll show you real quick. That's a good question, just to illustrate. If you open up the spec, so here's the spec, and if we go to chapter F, so this is in the back of the manual. So here's the CB term, here's where that's coming from, and for any time you're dealing with a W shape, C is 1, okay? If you're dealing with something like a channel, you calculate C, but pretty straightforward. So, but we're just restricting our discussion to W shapes, and since W shapes are symmetric this way and this way, like it's symmetric this way and that way, then C is 1. So, that's why we're just taking it. Everybody good with that? Sound good? Okay. Now I'm going to introduce you to the messiest design aid you've ever seen. Okay? The messiest design aid you've ever seen is table 310. Okay? All right. Let's take a look at this. Here's an image of the LTB flow chart right here. This is an image of it. And what I've done is I've taken that flow chart and I've plotted it, right? So I've got, if you're in zone 1, you've got the plastic moment capacity, BMP. If you're in zone 2, you have the linear interpolation. If you're in zone 3, you have what we just did. I mean, this right here is literally what we just did, right? Okay, here's the problem, all right? This is the flow chart, okay? But the flow chart, or the model that we use, let's put it like this. The model that we use to compute the flexural capacity of beams is a function of multiple parameters for a given beam. Like in order to fully plot this, we need RTS, we need J, we need SX, we need LP and LR, we need BMP, right? In order to plot one curve for one beam, we need all sorts of different parameters, okay? This is a different problem than when we were dealing with columns. With columns, there really was only one parameter to plot the curve, and that was R, or the minimum R, right? As long as you had R, you could totally plot the curve. But for beams, there's too many variables, there's too many parameters. See, the beauty of columns was we could use a single, literally a single curve for every column in the manual, because all you needed is an Fy and an R value. Can't do that to beams. Just too many unknowns. Since we cannot plot a single curve for every beam, the only way to effectively design is to use every curve for every beam. Okay? So that's what this is. Okay? It looks like a hot mess. I know it does. This is a lot easier to navigate than you would think, though. Okay? This is table 310. Okay? Table 310. What is table 310? It's just this curve right here, this curve plotted for every beam all on top of one graph. Okay? And it's kind of a mess. Okay? But I'm going to show you how to use this curve, or how to use this chart, and it's going to be a lot easier than you would think. Okay? So the way it works is we have the unbraced length on the x-axis, and on the y-axis we have the moment capacity. Okay? The moment capacity either in ASD or LRFD. So we're using LRFD. Okay? Now, this design aid only works if you have 50 KSI steel and if CB is 1, okay? More on that later, about what happens if CB is not 1. Today is just introducing you to this curve. Okay, now eyes up here, because I got a nice little animated slide that I prepared that shows you how this works. So this is my nifty little animation. Okay, so watch this. All right, so here's how you use table 310, okay? So the first thing that you have to do is you have to divide out the effects of CB. So all that means is you analyze your beam, and if CB is 1.2, you just divide the maximum moment by 1.2. All right? Then you find your point that you're interested in. Your point is on the x-axis, it's whatever your LB is, and on the y-axis, it's whatever your maximum moment is divided by CB. Okay? And then what you do is you look up to the right and find the first solid line. So watch this right here. Okay, so let's do a quick example. Okay, so I've got an LB of 28 feet, and I have a moment of, we'll call it 1162. Just made up these numbers. So what do? Boom, I find that point. Okay, so that's the point that has an unbraced length of 28 and a moment of 1162. Okay. What I am saying is that everything there is a safe design, okay? Because everything in that shaded region either has a higher moment capacity or it has a longer unbraced length, which is going to, like, If you have a beam that's strong enough to withstand a 28-foot unbraced length, it can withstand a 30-foot unbraced length, because as unbraced length goes up, capacity goes down, okay? So what I am saying is this. What you do is you look up and to the right and you find the first solid line, okay? So in this case, we would try a W27 by 146. That's how the aid works, okay? Now, some of you might be asking, why a solid line? Why am I picking the solid line? Does anybody notice something about the solid lines in this region? Like, look at these shapes right here. Like, let's just look at these three shapes. Can anybody tell me what's unique about the solid line as opposed to the dash curves?
It's the lightest.
It's the lightest, right? So remember how in table 3.2 the top row was bolded, and that top row that was bolded corresponded to the lightest shape, right? Here, if there's a solid line, it's the lightest shape within that family, within that region, okay? What I am saying also is that it is possible that the solid line here does not correspond to a bold row in this table, okay? That's why the example we just did was a W14 by 61. That wasn't a bold row. Does that make sense? Everybody okay with that? So I want to make sure that we're comfortable with this. So today, I want you to find this. Okay, so this is what I want you to do. I want you to open up to table 310, and I want you to find a shape for an unbraced length of 14 feet and a moment of 2150. And I want you to find the lightest shape within that region. I'm going to do it with you. 14, 2150. Let's see. I got my shape. I want to see how you all are doing. And again, we got plenty of time. The whole point of this is to get comfortable with this aid, because I know this aid looks like a hot mess. Where's yours? There you go. You can all keep in mind the labels might be above, so. You brought your manual, right? You have the manual. You brought the manual steel sign. The class that uses the steel.
Yeah, I have it. It's just a
Fitting, huh?
Yeah.
There you go. There we go. You might find your labels up here, by the way. How are y'all doing? Because you both brought the manual, right? You both brought the manual. You're just helping each other out. You look like you're in the right spot. Yep. Yeah, I think you found it. Where'd you find it? Yep. Did you find it?
Yeah.
So, now hold on, so it's 20, it's 2150, so you wanna go.
Oh, shoot.
Yeah, you wanna go back, there, so it's about right there. Did you find it? No, okay, so, what I was, can I see your hand? So, are you using the green numbers? Use blue numbers. That's probably it. Yeah, so, it's right around here, but it's on right there, so 14, about there, then this, there you go. Let's see, did you find it? Yeah. Yep. You find, yep. Found it? Yep, you found it? What's that? So, you're on the right page. Okay, so 2150 is about right there. Then L over 14. So you're about, so like, this is the point, about right there. Okay, so you're gonna track up, and it's this curve right here, which is a W40 by 167. You see that? So this is W40 by 167. Is everybody able to find this? Everybody good? We're gonna be looking through this chart a little bit, okay? Like for a few lectures this week. So I wanted to make sure that you're familiar with this, okay? And by the way, since we're on the topic, one of the things that I've mentioned for some time is that these design aids are necessary, or so necessary for steel design, that you will find them within the FE reference manual. Let me see if I can actually pull that up. Let me see, hold on. So let's see if I can log into my NCES account. Let's see if I remember my password. I have it stored, but not here. Hold on. Is that it? Nope. Let's try this password. Okay. Give me one sec. This is important. I really kind of want y'all to see this. Sorry. Give me one sec. Try this password. I think that's it. That'll do it. Okay. So if you log into your NCES account, which hopefully you all have created one or are on your way to creating one if you're planning on taking the FE exam, over here on the right here under Common Tasks is View Reference Handbooks. So if we click View Reference Handbooks, I'm going to go to the FE Reference Handbook, and so when you're taking the exam, this is the searchable PDF that you can use, okay? This PDF, by the way, is just useful, so I really think it's worth checking out. How many of you have not looked at this? Okay, let's just take a look at it for a second, all right? Let's go to civil engineering. Would it have been nice to have all these soil phase relationship formulas all in one spot, like your dry unit weight, your void ratio, your porosity, remember all that stuff? I know you know this stuff, right? So this, if you go to the civil engineering section, this is all the formulas necessary for the FE exam, but this is honestly just kind of a nice reference to have. Like we've got relative density, degree of saturation, here's all our consolidation, settlement calcs, C sub C, C sub R, all that stuff. Let's see, we've got our time factors. Y'all have seen this before, right? If you're in soils, I know you've seen this stuff before. More Coulomb failure criteria, tau equals C plus sigma tan phi. I know y'all know that. Let's see, we've got our horizontal pressures, Rankine and active, all that. Vertical stress. Soil classifications. Please tell me this is familiar, right? I know it is. All right, structural analysis, influence lines, truss deflections, rain deflections, all that. Okay, we get into structural design. Okay, we've got our ASCE7 load combos. This is getting into some wind load stuff, which we didn't really have time to discuss this semester, but how about this? Let's see. Let's get into steel design. Steel design. Well, look at this. We're already starting to see some stuff that's kind of familiar. We've got columns. Hold on, let me go back here. That stuff should look familiar, right? It's not like we haven't used this before, right? Okay, but check this out. So if we go into the design aid section for steel, what do we have? Okay, so the first thing they give us is some basic properties of some W shapes. So they give us a selection of W shapes and give us the area, the depth, flange, all this stuff. They don't give us everything because you don't need everything for the FE exam, but they give you enough that you can do the calculations necessary for the exam. What else do they give you? They give you, look at this, they give you the ZX charts, right? So the ZX charts, remember the top row is bolded. They give you ZX, PMP, PMR, BF, LP, LR, all this. Again, they don't give you everything, and they don't give it to you for every shape, okay? But they give you enough to negotiate the exam. And notice how they're only giving you LRFD terms. No green numbers and blue numbers, just the blue numbers, okay? So let's see. Look at this. They actually give you a snippet of table 310, okay? Not pages and pages of it like are in the manual, just enough to be able to negotiate problems on the test, okay? And again, what do? Line up here, boop, find your solid row. Here's one that should be familiar. We've got our K values for columns, and look at this. Look at this one. This is table 4.1, okay? It doesn't look the same because, again, everything's just LRFD, but here's your W14 sections, here's your W12 sections, here's your W10 sections, okay? And again, it's just the blue numbers, that's why there's no shading. So, again, it's all here, okay? So, I just wanted you to see this because when you open the exam, I don't want you to see this, and because it's formatted differently than what you see in the manual, that it's a different A. No, it's not. I mean, this table right here, if I go, for example, to table 3.2, this is the same table that's in your manual, same one. It's just formatted a little differently. So, yeah, they give you this stuff too. It's that important. Okay, let me stop for a second to see if anybody has any questions. Everybody good? All right, so what I'm going to do for your homework assignment tonight is I'm giving you a beam. Let me pull this up. 6.5. Yeah, okay. So what I'm going to do is I'm going to give you a problem. I'm giving you a W18 by 35. I'm going to have you analyze the beam. If it has an unbraced length of 10 feet and its CB value is 1.5, I'm going to have you determine the moment capacity. Then I'm going to have you do the same problem again if LB was 15 feet and CB was 1, okay? So it's the same beam, I'm just having you analyze it for two different cases. So one of them has a CB of 1.5 and an LB of 10. The other has a CB of 1 and an LB of 15 feet, okay? So two problems, but all on the same beam. And then we're going to get into design mode, okay? We're going to do two different types of discretely braced beam designs, and there really aren't two types. I mean, it's just, just designing beams. But I'm going to separate those into what I'm calling low CB value problems and high CB value problems. And there's a difference between low and high. You'll understand what I mean. We're going to start out with low, and then when you get familiar with that, you get into high, you go, okay, I see what he's talking about. Okay. That's all I have, everybody. I'm going to pull the code up one more time, and I will see you all on Wednesday. Enjoy the eclipse.